So today we'll continue our discussion of Module 4 as a part of bridges. Let us see first what we mean by bridge here. Bridge is a circuit or network of resistive elements as shown in this figure. It is energized either with DC source or AC source. So as you can see here, DC source E is connected with the switch SW1 between the points A and B. Before switch SW1 is closed, galvanometer G, that is now used as a detector, that is a current detector connected between the points C and D, should be properly calibrated. Means we will have to ensure that the pointer should be exactly in the middle. Later, depending on the unbalanced condition, the pointer will show the deflection either to the left or to the right side. So zero condition will be indicated by the middle one. Now you can see in this circuit diagram, four resistors R1, R2, R3 and R4 with R4 as unknown resistance is connected. So when switch SW1 is closed, after calibrating the galvanometer, the main current in the circuit at point A is divided into I1 and I2. And similarly, I3 and I4 are the currents flowing through R3 and R4. So how to measure the unknown resistance here? So to measure the unknown resistance R4, one of the three remaining arms will be made adjustable one or a variable one, so that we can vary that resistance. For example, suppose R3 is made variable one, then R3 is supposed to vary in order to match with bridge balance condition. So that will ensure that the potential difference between C and D will be zero. Then the galvanometer pointer will be exactly at the middle. That is known as a balanced condition. Means the balanced condition is indicated by the pointer in the middle. Otherwise, the pointer will be either in the left or right side of that middle of galvanometer. That is indicating unbalanced condition of the bridge. So why we have to go for this bridge circuit in order to measure the resistance? Because we have seen in the digital multimeter, it is also going to measure the unknown resistance. That will directly give you the value simply by connecting it in the circuit. So the bridge is more accurate compared to the digital voltmeter. That's what the reason they quote. This is because it is comparing the unknown resistance with the standard one. Standard resistance value with the standard resistance value, this unknown value will be compared, so that there is no any room for the error. If it is a 2 ohm, we are exactly getting the measurement of 2 ohm. So error is drastically reduced. And moreover, the measurement or deflection of the galvanometer, the measurement of the unknown resistance is dependent, not depending on the any characteristics of the galvanometer that it is showing the deflection. So galvanometer is the main element that is detecting whether your bridge is balanced with a zero condition or null condition in the middle, or unbalanced on either side of the deflection. Understanding? So that's why. So that measurement of unknown resistance is totally going to be independent of the deflection or characteristics or properties of the galvanometer. Means measurement of unknown resistance is independent of this galvanometer. So that's why we can say the measurement of resistance by the bridge circuit is more accurate compared to the digital voltmeter. Now let us see the Wheatstone bridge, that is a measurement of resistance. The same circuitry I am using here. The figure shows a typical diagram for the Wheatstone bridge with the four resistive arms R1, R2, R3 as known resistances, with one of its R variable, and R4 as unknown resistance. DC source E is connected in series with SW1. Before SW1 is closed, galvanometer G is properly calibrated with its null indication exactly in the middle. That is indicating the balanced condition of the bridge. So this will be ensured before this SW1 is closed. The moment when you close the switch SW1, the current from the E is divided into I1 and I2 at node A. Similarly, I3 and I4 are the currents flowing through resistive arms R3 and R4. So operation is very simple. When switch SW1 is closed, so we can say the bridge is balanced if the current, the voltage at point C and voltage at point D are same. Voltage difference between the C and D is zero. Means same current is flowing on either side. That is indicated by the null condition of the galvanometer. Otherwise, galvanometer is showing a deflection on either side, left or right side, depending on the direction of the current. That's what has been explained in the form of operation. So the bridge balance equation, how to achieve that? So bridge balance equation has been shown here. You can see here. That is Rx equal to R2 R3 by R1. So this one, Rx, this was R4 if you take it as Rx, R2 into R3 divided by R1 will give you the equation unknown resistance. So let us see how to obtain this bridge balance equation in case of Wheatstone bridge. So referring to the same figure, when SW1 is closed, the current flows and divides into I1 and I2. So hence you can see current I1 and I2 we are getting. So voltage drop across R1 and R2 are going to be same. Equally it is divided. So we can say I1 R1 equal to I2 R2. So we can write this one. Equation number 1. I1 R1 equal to I2 R2. For the galvanometer current to be 0, means only when the galvanometer current is 0, we can say that the bridge is balanced. Otherwise, it is imbalanced. It is showing some deflection. So we can write two currents here. One is this I1 and I3. If you look at this switch SW1 closed, so we'll get this one loop starting from E, SW1, A, R1, C, R3, B, and E coming back to E. This one closed loop. With this closed loop, we can write an equation for the current I1 and I3. That is equal to, so this is the series circuit, so I1 and I3 same current it is. So we can write I1 equal to I3. So by ohms we can write I equal to V by R. What is the voltage in this loop? Capital E. That is divided by total resistance R1 plus R3. So that's what we are writing as a part of equation number 2. I1 I3 equal to E divided by R1 plus R3. Similarly, we can write I2 equal to, so this outer loop, if you look at this one, this outer loop starting from E, SW1, A, R2, D, R4, B, and coming back to E. So this I2 and I4, again it will indicate a series circuit. So therefore we can denote this as I2 equal to I4 with E as a source, E divided by R2 plus R4 we can write. So this is the current equation as a part of equation number 2 we are writing. We got two set of equations in 2. Now using 1 and 2, we can substitute for I1 and I2 here for these things. So what we can get E R1 by R1 plus R3, because I1 is E R1 E divided by R1 plus R3. So this R1 will be remaining as it is. So I2 is nothing but E divided by R2 plus R4. So E divided by R2 plus R4 into R2. Now if you cross multiply this one, E R1 into see similar things you get it cancelled E on either side. So only left out here it is R1. Cross multiply here R1 into bracket R2 plus R4. So here also you cross multiply R2 into bracket R1 plus R3. So similar things you get it cancelled. As finally we are getting R4 equal to R2 R3 by R1. So this is the standard bridge balance equation for the Wheatstone bridge. R1 R4 equal to R2 R3. So let us see what are the R1 R4. So one thing you remember, R1 R4 opposite pair are there. R2 R4, R2 R3 another opposite pair. You see this one, R1 R4, R2 R3. R1 R4, R2 R3. So this you keep in mind when you do doing the derivations or any problem or explaining the operation in the bridge. The main you people are confusing here is that, so this topology you have to remember, R1, R2, R3, R4. So fix one this thing you keep in mind, or you should be very much confident that whatever the topology you can follow, it may be R1, R2, R3, R4 or whatever, should get the accordingly the correct bridge balance equation. So for this order R1, R2, R3, R4, we got it as R1, R4 equal to R2, R3. Whatever may be the arrangement, it may be R4, R3, RT, R4, whatever. So we'll get always the bridge balance equation as opposite pairs, product of opposite arms equal to product of another opposite arm, like that. Whatever may be your arrangement. Or else you remember this order always, R1, R2, R3, R4. For this you are getting the bridge balance equation as R1, R4 equal to R2, R3. So this we have seen so far how to define the bridge, explain the why the bridge is more accurate than the DVM. In Wheatstone bridge we have seen the construction, how we have to do calibration before closing the switch SW1. After closing the SW1, how the currents we are getting, how the bridge could be balanced with the help of null condition in the galvanometer to be balanced, and also that balancing is achieved with the help of bridge balance equation. And also we discussed how to obtain bridge balance equation for the Wien bridge. Now let us see the sensitivity, what you mean by sensitivity of the Wheatstone bridge. This is nothing but the amount of deflection shown by the Wheatstone bridge or the galvanometer per unit current. So that's why its unit is going to be amount of deflection it is there, that is measured in terms of millimeter or degree or radians per some current microampere, like that. So the sensitivity is given by this formula, the relation between the sensitivity and the deflection. D equal to, that is a deflection, total deflection, that is equal to sensitivity into the current in terms of microamperes. So let us see how we can balance it out, the Wheatstone bridge, with the application of the Thevenin's theorem. So unbalanced Wheatstone bridge, the amount of deflection can be decided by applying the Thevenin's theorem. So by Thevenin's theorem, all you may be conversant with this one. So VTH normally we can estimate with open circuited voltage. You can see here where we connected the galvanometer to measure the amount of voltage difference between these two nodes. Now it will be open circuited. Okay. So because we need to calculate the VTH, that should be open circuited voltage. So with these two terminals open circuited, we have to find out equivalent resistance. That is a Thevenin's equivalent resistance between the points A and B. So with this, what we are getting equivalent voltage, how to calculate that one. Let us find out EA here, voltage at node A. Voltage at this point A or A here, both are same because that is open circuited. So voltage at point A, that is EA, equal to, so this slope we are getting here, this slope. So E divided by R1 plus R3 is the amount of current flowing through this loop into R3. That is one resistance you can take. Similarly, the voltage at point B, nothing but V equal to I into R. What is the current? E divided by R2 plus R4 is the total current into through which resistance this current is flowing through R4. So that will be EP. Now to find out VTH, we have to take the difference VA minus VB. Simply you take EA minus AB, manipulate, resolve it, and finally we are getting Thevenin's equivalent voltage as E into bracket R3 by R1 plus R3 minus R4 by R2 plus R4, like that. So this is Thevenin's equivalent voltage you got by open circuiting the galvanometer. Similarly, we can get Thevenin's equivalent resistance by short circuiting it. Means here the galvanometer should be replaced by its a very small internal resistance. That is called as short circuited resistance. It is very small, inherent to the galvanometer. Now the circuitry will look like this. So we have to find equivalent resistance here with the short circuiting the galvanometer and replacing it by very small resistance. Short circuit means it is a very small resistance. So these things are coming now in parallel because of this short circuit. So what we can RTH hello. So now you can see R1 is in parallel with R3 and R2 is in parallel with R4. You can add these two. So these two are in parallel, coming in series with R2 with. Finally, what you are getting RT is equal to R1 R3 by R1 plus R3 plus R2 R4 by R2 plus R4. So you can represent now your whole this bridge circuit into its Thevenin's equivalent circuit as ETH connected in series with RTH. ETH. So this is like a voltage source because ETH is the Thevenin's equivalent voltage source connected with the resistance RTH. This is acting like a voltage source here. How to find out the unknown the deflection here, amount of deflection. So that galvanometer connection is coming. The galvanometer is now connected across A and B. I will have deflection. Will have some deflection at the foot of the bridge. Deflection current in the galvanometer is done by like this. Suppose if you connect the galvanometer here, no. So having some internal resistance RG, then what you can get that in that total loop, the current what you are getting, the current flowing through the galvanometer Ig, that is equal to ETH divided by total resistance RTH plus RG. Now let us take the problem here. Calculate the current through the galvanometer in an unbalanced Wheatstone bridge here. So values are given here with a 6 volt DC supply. R1 is 1 ohm, 2 R2 2.5 kilo ohm, R3 3.5 kilo ohm, and R4 also given 10 kilo ohm. So we have to find out some bridge parameters here. So how to get the Thevenin's equivalent circuitry for this one. First, we have to get the ETH. So ETH, we can get it here by open circuiting it between the points A and B. That is A minus AB. Directly, now we have the formula here. We can use this one. Provided, hello, okay. Provided you are going to follow this arrangement R1, R2, R3, and R4. With respect to that, we got that one. So you can substitute the values here. You can get 88.132 volt. Similarly, we can use the formula for RTH. Substitute the value with this arrangement R1, R2, R3, and R4. We can get it as 2.778 kilo. Now, once you get ETH and RTH, we can draw the Thevenin's equivalent circuit, connect the galvanometer with RC 300 ohm. We can get the galvanometer current, substitute all the values, that is a 42.88 microampere. So this is how in examination we will be giving you the bridge circuitry with all known values and asking you to find out the galvanometer current. Next, let us consider another version of the Wheatstone bridge, where a slightly unbalanced Wheatstone bridge we can call. Means, so 3 arm resistors in the bridge are equal to R. They are equal in values totally. And the fourth arm just got increased by a slight amount by delta R. That is 5% is not telling. Now voltage at point A, again we follow the same Thevenin's equivalent circuitry rules here. So voltage at point A is nothing but is equal to total current here E divided by 2R, R plus R 2R into R. That is E by 2 will get. Similarly, EB you can get voltage at point B. E total current is going to be E divided by R 2R plus delta R. 2R, this R and this R, 2R plus delta R into the resistance through which this current is flowing, that is R plus delta R. So you can substitute these values to get the ETH. So finally we are getting ETH this much. So with the delta R 5% of R or less, we can get with this substitution ETH equal to E in delta R. Similarly, we can get RTH by replacing the RTH. Hello? Okay. RTH can be obtained by replacing the voltage source with its internal resistance. So this one. So this should be short circuited. If you follow the steps that like that, so these two are running in parallel. All are R here except R4, that is R plus delta R. So how we can get? R and this are going in parallel. That is, you can calculate how much you will get. R by 2 will get plus R in parallel with R plus delta you can calculate. So if you do that one with pen and paper, so finally we are getting RTH equal to R to R plus R divided by 2R. Hello? Hello? Yes. So with the R, because we have only 5% variation of the total R. So R is delta R is very small, then and finally let us take another problem. Hello. Let us consider another problem. Give a center 0, 200, 0, 200 microampere current. Means your null condition is at 0, and on either side, depending on the clockwise or anti-clockwise flow of the current, deflection is going either towards the left side up to 100 microampere or towards the right side up to 200 microampere. Having internal resistance 125, that is RG is given, and the current in given figure by approximation method. This is another slightly unbalanced Whitson bridge is also known as approximation method. So approximation method will come into picture when all resistance is 3 hours, 4th hour by 35. Now student is here in each art, whatever the formula. So I see finally you are getting this formula. So how you can work on at home. So to become no, you can go to the hello. You can go through the application and you can see some applications given Whitstone bridge used to measure DC resistance of different type of wire. May be useful for the quality control of wire or some assembly in which it is used. For example, resistance of motor windings or transformers or solenoids like that. Can also be used for telephone companies to locate the cable faults. So the limitations are not useful for the low resistance measurement like leads or contacts. Not useful for the very high resistance measurement. Therefore, high resistance measurement the mega ohms, in terms of mega ohms, Whitstone bridge cannot be used. Rise in temperature can affect its performance. These are some limitations of the Whitstone bridge. So today we have seen how to define the bridge, how bridge is more accurate than the DVM in measuring the resistance, how to explain the structure of the Whitstone bridge structure, its operation also we have seen, and how to derive the Whitstone bridge balance equation. We have gone through some simple problems, and also we have applied Thevenin's theorem there to obtain Thevenin's equivalent circuitry for the unbalanced Whitstone circuit. And by that, we came to know how to calculate the unknown galvanometer current. And also, we have seen slightly unbalanced Whitstone bridge special case with 3 arms equal, 4 arms given with a slight balance. Now, next one, we can, so far we have seen Whitstone bridge is a DC bridge. Now, AC bridges, under AC bridge, instead of DC, now we are using AC source.
And instead of resistive arms, now we got impedance arms. Impedance, impedance arms are there. Z1, Z2, Z3, and Z4. And instead of galvanometer, now I am using headphone. So its function is similar to the galvanometer. In galvanometer, the bridge balance is indicated by the null indication. But with the headphone, we are going to listen no sound. Means when bridge is balanced, we are not going to get any sound here or noise. So that is the main difference between the DC and AC bridge. Okay, are you getting this one? Yes. So Z1, Z2, Z3, and Z4 are impedances, means they are maybe purely resistive or they may be resistive reactance or resistive arms may be there. Okay. So therefore, it is necessary to adjust both magnitude and phase angles of these impedance arms. Suppose if one of your arm is containing capacitance, so because of the reactive elements like inductance and capacitance, phase will come into picture. Because resistance phase, the phase will be there. So we need to adjust magnitude along with the phase in order to adjust the pitch. Now let us see the capacitance comparison bridge here. As you can see here, in case of capacitance comparison bridge, it consists of first arm is variable resistance R1, second arm is fixed R2 resistive value, third arm consists of C3 connected in series with variable R3, and fourth arm is unknown, that is Cx in series with Rx. So accordingly, we'll have to explain here. So detector, that is headphone, is connected between these 2 points. So when you connect the AC source, so bridge will be got unbalanced because of this unknown arm and will start getting the noise. Now we'll have to vary R1 and R3 so that we will get noise reduction. When you will get zero noise, we can say the bridge is balanced. So this is how you have to explain about structure and operation. Now let us derive the bridge balance equation. Now you can see R1 is a Z1 is R1 purely resistive, Z2 is R2, Z3 is R3 and C3 combination is there. So I can write it like this, R3 minus J by omega C3. In the same way, Zx is going to be Rx minus J by omega Cx. So bridge balance equation, how we can write? Z1 into Zx, opposite pairs. Z1 into Zx equal to Z2 into Z3. Z1 into Zx equal to Z2 into Z3. We can substitute the values here. Z1 means R1, Zx means Rx minus J by omega Cx, substitute here. Z2 equal to R2 into bracket. Z3 means R3 minus J by omega C3. Now we can bring these terms outside the bracket. R1 into Rx minus this R1 is got multiplied with J by omega Cx. We'll get it as J R1 by omega Cx, that is equal to R2 into R3 minus R2 into J divided by omega C3. So this is how you have to expand the brackets. Now what we can do, because of the presence of J is now treated as complex term. We'll have to separate out these real terms and complex terms or imaginary terms separately. Separately, we have to compare. So comparing the real part separately, what will get? R1 Rx equal to R2 R3. We'll get it as Rx equal to R2 R3 by R1. Separately, if you compare imaginary parts, we can get it as R1 by omega Cx equal to R2 by omega C3. That is Cx equal to R1 C3 by R2. So this how we have to get the design equations for the Rx and Cx. So in examination, he will ask you to a capacitance comparison bridge used to uh, to measure capacitive impedance at 2 kilovolts. Means frequency is given. The bridge constants are C3, R1, R2 and R3 are given. And now he is asking you to find equivalent series circuit of unknown impedance. So you got the design formulas Rx equal to R2, R3 by R1 that you can substitute here. R2, R3 are given. R2 is 50 kilo ohm, R3 is 100 kilo ohm divided by R1 divided by R1 10 kilo ohm that you can substitute and use the calculator. So we'll get unknown resistance Rx equal to 500 kilo ohms. So don't forget to write the end units. Next, simply you can substitute the values in the Cx formula to find out Cx value. That here we got it as 20 microfarad. So as he has asked in the problem, find the equivalent series circuit. So simply draw this one with the known values. So unknown values, whatever you got, that's all. So this all about capacitance comparison bridge. Similarly, we got inductance comparison bridge. So here you have to remember the bridge arm circuits clearly. So here the first arm is again Z1 equal to R1. Second arm again Z2 equal to variable R2. Z3 instead of capacitance now we are getting variable R3 in series with L3 and unknown again Rx and Lx instead of capacitance because it is inductance comparison bridge. Similarly, if you follow the same things, same steps, we can get the design equations Lx and Rx for these things. You can follow the same steps as we did here. So that is a homework. You can work it out. You can easily get. So similar problem will be given. An inductance comparison bridge is used to measure inductance impedance at 5 kilowatts. The bridge constants are given L3, R1, R2, R3. And now is asking you to find out equivalent series circuit of the unknown impedance. Simply all the values are given, but you have to solve it neatly like this. Substitute the values here to get Lx and Rx and draw the final this arm. Don't forget to draw that one. So that's all. So next one is a Maxwell's bridge. I'm not sure whether it is there or not, but we'll cover that also. Maxwell's bridge. So here the first term is a complex one, variable R1 connected in parallel with C1. Z2 is going to be R2. Z3 is going to be variable R3 and Z4 is going to be Rx and Lx. Similarly, we can write Z1 R1 in parallel with 1 by j omega C1 like this one. Z2 equal to R2, Z3 equal to R3 and Z4 equal to Rx in series with Lx. So we can write it as Rx plus j omega Lx. With the bridge balance equation, Z1 Zx equal to Z2 Z3. So like this one. So for Z1 you can substitute the parallel combination of this one and Zx you can substitute this one equal to Z2 Z3. If you simplify like this, finally you are getting the design equations for the Rx and Lx like this with the quality factor Q equal to omega C1 R1. So the advantages of the Maxwell's bridge are its measurement is going to be independent of the input frequency. The scale of resistance can be calibrated to read the inductance directly. So the limitations are measurement is limited up to the low Q values up to 1 to 10 only. if the Q value of the wire which needs to be measured is more than 10, no, then Maxwell's bridge cannot identify its or measure its inductance correctly. Due to fixed capacitor, there is an interaction between the resistance and reactive balances. But this problem can be avoided by varying the capacitances. So let us consider another problem related to Maxwell bridge. So all the values are given here. So the problems based on the bridge are very simple. Only thing you should ensure which arrangement or pattern we are going to follow for all the bridge arms. Accordingly, you have to get the bridge balance equation, and accordingly you have to use the correct formula here. So you can substitute, so directly I have given you the answer here, you can work it out. So the next one for the discussion is a Wayne bridge. In Wayne bridge, Z1 is nothing but R1 is connected with C1. That's why we can write it as R1 minus J omega C1. Z2 is nothing but R2. Z3 is nothing but R3 in parallel with C3. And Z4 is R4. So that's why we can write Z3 instead of Z3, because this is the parallel combination is there, I am going to write it as Y3, admittance. It is a reciprocal of impedance. Reciprocal of impedance, I am taking it as admittance. So R3, that is Y3, that is 1 by R3 plus J omega C3 you will get. Again, you use the same bridge balance equation Z1, Z4 equal to Z2, Z3 to obtain final design equations for this Wayne bridge. So we are getting the frequency for the Wayne bridge along with the design equations as shown here, A and B. So let us consider the problem here. Then the Wayne bridge circuit with the following constant values. Find out the frequency. Simply substitute the values, we will get it. That is a very simple problem. But use the calculator correctly and never forget to write the end units. So in this another problem, find the equivalent parallel resistance and capacitance that causes Wayne bridge to null, means balance. So first with the given frequency, here you have to find out omega. This is very important, guys. Without omega, you cannot calculate R3 and C3 because they will depend on the omega here. Once you get omega, all the things are given, you substitute, you will get the R3 and C3. In the same manner, another problem I have given, you can practice at home. So here let us stop. With this will wind up your module 4. So you can practice at home.